Welcome everyone to this lecture. So we are going to basically begin with the idea of pressure in a gas. Um, so basically we are currently doing kinetic theory, and in the last video we discussed what were the key assumptions um in that theory. So let's begin. One of the important things which we basically remember uh, from that particular lecture is that the particles in a gas follows Newton's law. So we can calculate things like momentum and change in momentum. So even though they are very small particles, they exert some force on whatever objects they encounter, including the wall of the container. So first, we want to define how fast the particle is moving. Only then we will be able to figure out that what is its change in momentum. So we define a quantity called root mean square speed for a gas particle. So this RMS speed, for in short, it is called RMS. RMS speed. Um, it is defined to calculate that velocity of a particle which shows some kind of average motion of all the uh, particles. So the key term which I said is average motion. Uh, Mathematically, if I just simply add the velocities of all the particles, then the all the velocities in gas of the particles would simply add up to zero. But that is not what we want. We still want some kind of average value or some average speed with which the particles are moving. So how do we figure that? So we have a nifty technique by which we square the speed of the particles. After squaring the speed, we basically add them up, adding all the speeds. Then we take a mean of them and basically repeating what I'm saying. If I have the speed of a particle, I square the speed of the particle. I add all the squares of the speeds which I have taken. I divide them by the number of particles which I have taken. That means I have taken average of all the squares. And then I take a square root of the whole thing to get a root mean square speed. So how we do that? How do we remember what we have done? Is by getting this order, by basically make a note of this order. We first square all the speeds. So speed of particle number 1 squared, speed of particle number 2 squared, and so on, speed of n particles squared, because each gas will have some n number of particles. We divide them by total number of particles and we take a square root. So this RMS speed is a key indicator of how fast the particles in the gas are moving. So this should be very important for us, right? We are studying microscopic particles, microscopic properties of a gas. So when we say the particles have a microscopic speed or microscopic particles have some speed, we want to know, okay, what is the variation in those speeds? What is done and what is an average values of those speeds? So this RMS speed is not exactly that average value, but shows one of the parameters of the speeds of all the particles. So its significance would be clear to us a little bit later, but it shows the distribution. Next, if I take a particle and it has speed in x, y, and z direction, I am taking three dimensions. So it will have speed in x direction, it will have a speed in y direction, and it will have a speed in z direction. So we took a what we say assumption that the distribution of the speeds of the particle in x, y, and z direction would be same for all the particles. So that means that if I take a square of the speeds of a single particle, square the speed of single particle in y direction, square the speed of a single particle in z direction, and I then add them up for all the particles in x, y, and z direction, I can say that all these summations will be equal, right? So this is from the assumption which we have uh, taken from kinetic theory, that the speeds of the particles in x direction would be same as the speed of the particles in y direction would be same as speed of the particles in z direction. I cannot directly say that vx is equal to vy is equal to vz, but what I can say is that if I take the sum of speeds of all the particles and their squares, then I'll get a equal value. This is what I can say. I cannot say for a single particle, I can say for all the particles. Then if I use basically this equation VRMS, so I will arrive that VRMS square is equal to this summation Vx square by n times 3. So this is one of the equations which we'll be using, right? Okay, now we are talking about what is the momentum of a particle. So let's say mass of the particle is some m, okay, and it is moving in x direction towards some wall, which you will see in the animation, towards some yz plane. So as it is moving with some speed vx, its momentum is m into vx. So mass of the particle is smaller, its speed in x direction is vx, so its momentum is m into vx. Now, after colliding, we are saying what was the collision which happens with the particle and the wall? So you would have guessed it, right? It's an elastic collision. So in elastic collision, change in momentum is equal to minus 2 mvx, where the negative sign shows that finally the particle has moved in the opposite direction of the original one. So this is my change. If I divide this change with the time taken Vx by time, so this will give me the force exerted by a single particle. So okay, this much we have obtained. So force by a single particle is 2mvx by t. Force exerted by all the particles in that t time of motion is equal to minus 2m summation vx by time. Right? That would be the force. Right. Uh, so now basically we have to get rid of this time factor, that what time it take to complete one collision. That is one thing which we have to consider. And next, how do we use this summation sign? Summation of all the velocities uh, in x direction. So if I want to use the expression of pressure, that what is the pressure exerted by all the particles? I would say pressure will be denoted by P. The pressure exerted by the gas would be this force F divided by L square. Right? Um, okay, fine. This F by L square. Now this L is the uh, length of the cube. Right? So that means the force becomes equal to minus 2m summation Vx divided by T into L square. So this is our pressure P. So we can drop the negative sign because we only need the magnitude of the force. Okay, fine. Now, in what time would have the particle traveled that particular distance? I would say that the particle is traveling with this Vx speed. It is traveling this distance L. So we will say that the total time taken T would be equal to 2L. That is the time taken by the particle in going from one side of the container to the other side, colliding and coming back. So that would be distance upon the speed with which I have gone would be equal to whatever time I have taken. So this P will be equal to 2n summation Vx square, because we will put the value of time here, divided by 2L into L square. So this is some m upon L cube into summation Vx square. So this summation sign basically we introduced one step earlier than it should have been, but this expression is fine. Now we'll say that this pressure P is equal to m into n divided by L cube into summation Vx square divided by n. And this expression summation Vx square by n that we have already calculated. Its value was Vrms square by 3. So we'll just put that value over here. So this is simply density into Vrms square upon 3. So this m is mass of a single particle, n is the number of molecules in the gas. So this is total mass of the gas divided by L cube. This is the volume of container. So mass of the gas divided by volume is equal to uh, the density of the gas. Uh, then we will say that this Vx square expression summation Vx square by n, we said that this is equal to Vrms square by 3. So we have just substituted that value here and we got this. So rho is the density of the gas. Density of the gas. So the finally expression which we have is 3 pressure 3p divided by rho uh, is equal to Vrms. That is the RMS speed of the particles in a gas depends upon the pressure of the gas, direct proportionality, and inversely proportional to the density of the gas. So more accurately speaking, we can say that the RMS speed depends upon the square root of pressure and inversely proportional to the density of the square root of density of the gas. So that's it. Thank you for joining.